usually when we, so usually when we want to select a separation mode, we will have to see whether the sample, is it volatile or non-volatile by looking at the boiling point. Yeah. So if the boiling point is below 500 degrees Celsius, so meaning that it is easy to be volatile. So if the boiling point is below 500, usually we will use GC as our separation mode. But if it's more than 500, for example, if the molecular weight is more than 2000, which is a big molecule, so usually we will use another method to separate big molecules. So in terms of big molecules, and after that, we have to decide whether this molecule, is it water soluble or not. So if the molecule is water soluble, so usually we will use GFC, which stands for gel filtration chromatography. Excuse me. So if it's not water soluble, maybe like a lipid or something, then usually we will use GPC, which is a gel permeation chromatography, as written here. So these two, the gel filtration and the gel permeation, it's under what we call SEC, size exclusion chromatography. I will share this XCC in our class next week. So today, we were going to talk about how we separate small molecules with molecular weight less than 2000. So in this case, well, there are a lot of separations interactions, but one of the most popular ones is the reversed phase. And secondly is the ion exchange, absorption, and partition. Yeah. So you might be wondering, why do I put absorption and partition here and instead of reverse phase or something? Well, actually, the main is actually the partition. Yeah. So like previously, we talked about the classification based on the mechanism of separations. Well, the main type, it's what we call absorption chromatography, or we usually say partition chromatography. So today, I'm gonna focus on these two. Yeah. All right. Just wondering, what do you know? Like, what do you think is the main difference between absorption and partition chromatography? Some people, well, sometimes it sounds the same, yeah. Like absorption or partition, it sounds the same, no? What do you think? Do you think they are the same, or do you think they are not the same? Just a random question, so it's okay if you don't know the answers, yeah. So actually, the mechanism is quite similar, yeah. So the difference is the support. Like in terms of absorption, usually we use for gas solid chromatography, or like last time we talked about thin layer. So thin layer chromatography is a form of absorption as well. And in our seventh time, we will talk about HPLC. So these three main types we call under the absorption chromatography in the beginning, yeah, in the beginning, because solid is used as a support. For partition, it is more like a liquid or gas, where we have to, like we have the diffusion, we have to have a diffusion between the gas phase and the solid and the mobile phase. So what we can say here is like the gas liquid chromatography, or we can say the liquid chromatography. And some people say paper chromatography is also under partition. Yeah. So it is, well, different people have different kind of perception of what we can say, whether paper chromatography is either partition, or we can say paper as a solid support can be an absorption as well. Yeah. But because paper is not as robust, as strong as other like a thin layer, where we use a glass or we use a silica gel. Paper is more like a cellulose, it's very weak. So usually we need to, it's more like a liquid base, you know, like when we soak or we just put the paper in another solvent and then we dried it. So in this case, some people say paper chromatography can be put under the category of partition. So in other words, if I would like to share this diagram, absorption is more like, you know, direct to a surface here of the support. Whereas partition, originally it is from liquid and liquid, but right now partitions has become one of the most important separation mode is because most of the separation is based on the partitioning of chemicals into a layer on the stationary phase. So, I mean, like theoretically, it is like this, like, you know, direct to the solid support. But in the case of partitioning, the liquid phase, a part of the mobile phase will form a layer on the support. And this layer of liquid with another liquid will become the interactions. So we call it the partition interactions. So if maybe in the first half of these lectures, maybe Amora or Busoja already told you about these liquid-liquid extractions using this separation funnel. So separation funnels, it's a very traditional type of liquid-liquid partition chromatography. Like usually we use water and hexane. So you know water and hexane, they are immiscible, right? They cannot mix together, right? So for example, this compound A is more water soluble. So a big portion of compound A will be dissolved in water phase. But in some extent, it is almost impossible to, you know, to achieve 100% into a certain water phase. Yeah? So a small part of this compound A will like being distributed, or what we call being partitioned in a small part of the organic phase, which is the hexane. And in the same case, when this non-water soluble sample, like a lipid or something, so usually it is easier to be dissolved in organic solvent, but a small part of it will still have some interactions with the water phase. So in other words, you know, this liquid-liquid partitions is the original form of partitioning chromatography. So at the beginning in 1952, when I talk about the history of chromatography, Martin was the person who discovered this partitioning mechanism, and he was given a Nobel Prize in chemistry in 1955 when he also proposed paper chromatography in the same year. And he was also the person who proposed gas chromatography. So he is a very important person, and I think he is the first chromatographer who were given a Nobel Prize in chemistry a long time ago. So anyway, and the advantage of using absorption chromatography, well, we can have many choices of separation modes as long as we choose a different support. We can choose silica, we can choose alumina, or we can even choose like aminopropyl. So we can have a good varieties of separation modes. And from all those choices, of course, we can retain and separate some compounds that cannot be separated by other methods. For example, separations of geometric isomers. So isomers can be very tricky because they are almost the same, but they are not the same. And geometrical isomers is rather easier. And then, but somehow it is a bit more complicated when we come to like the optical isomers. Yeah, so it is a bit more complicated when we want to do chiral separations for drugs or sometimes for food. And I will talk about that maybe in some other sections. So, but when we have advantages, of course, we also have disadvantages. So I don't know whether I should say this is a disadvantage or not, because when we have a very good retention, sometimes when the retention or the absorption is too strong, it takes too much time to do the analysis. Yeah. So that's why sometimes when we want to separate, for example, amino acid. So amino acid, it's basically it's a weak acid. If we use a strong ion exchange column, it will take a long time to separate them, especially when we have so many amino acids, like it, well, naturally in our body, you know, we cannot produce a lot, but like minimum, we have like 20 kind of different amino acids. But in the real time, when you want to do a screening, or usually we do a screening for different drugs. So in this case, when the absorption is too strong, it takes too much time to do the separations. But at the same time, it is complicated, yeah, because we want to have good separation, but at the same time, we want fast separations. You know, human being, we are so greedy. Yeah? We want it good and then we want it fast. We don't want to wait. So there is a time now, a lot of people has been trying to make good columns, which is quite difficult actually, because we have to fight with the pressure and also we have to fight with the packing. By the way, last week, some students asked about packing column. So I brought some of the column like this. So these are the two HPLC columns actually. Maybe it's difficult to see. This is the normal type, which is 4.6 mm. This is a bit smaller, thinner, and it can separate faster. It is same length here, 30 centimeters, but this one is bigger, which is the conventional type. This is the new type, yeah. So it's produced by this company. So both of them are silica columns. So some students ask what happened when there's a peak, like an overlapping peak. And sometimes you have the peak, which is like asymmetry, like you have a broad peak. So usually when you have a column flow like this, sometimes when the column is old, you need to wash the column, yeah. But sometimes you need to open the column and to fill a little bit on top of here. So, sorry. For example, when you open the column, I use a bigger one so that it's easier for you to see. So when you open the column, there will be something like an empty space like this. So usually we will do the packing by ourselves in my lab, because my major is making columns. So we pack ourselves and then we also repair column by ourselves. So sometimes when you have bad separation, like an overlapping, like a tailing, like a fronting, when your peak shape is not good, sometimes at the beginning of this part, there's an empty space here. When there's empty space, when your column, when your sample go to the column, sometimes some broadening will happen here, even though it's a small part, but sometimes it will affect your peak separations. So you can send the column back and ask for a repair, or you can buy a new column, which is not so cheap. So usually I will repair myself. So we will just, you can, it's not so typical, yeah. Just make sure you don't open when the column is too dry, yeah? Because when the column is dry and you open, the powder will disperse and then you will happen to suck the powder, so which is very bad. So in this case, make sure you wet your column first, and then you can open it. By using a different bench, you can open the column very easily. Yeah? So when you open it, and then you can just top a little bit of your packing materials. Yeah. So usually Usually when the column is old, I do not throw them away. I will open and I will keep the inside the packing materials, because the packing materials usually is very strong and you can reuse many times. Yeah. So once the column is old, don't throw it, open it and take it out. You can wash it with methanol and you can dry it and you can use it again. Yeah. So by keeping these old packing materials, you can use it for repair for your new column sometime when it is not so good. Sorry, this is just because last week I couldn't show you the column, so this time I brought the column to show you the column. Anyway, I will continue with today's slide. So the disadvantages of using the absorption chromatography is a very strong retention of some solutes. And sometimes the too long retention time, or sometimes the non-symmetrical peaks or variables of retention times. This is because the solid support may have a range of chemical and physical environments. Yeah? So because it's a solid, yeah. So when we use a different solvent, so the chemical or the physical environments of the support will change. So that's why when we want to make a new column, we have to use a very stable support. At the moment, silica gel is still the most, we said it, the most stable in terms of separations, but silica gel is not stable in pH more than 8 or sometimes more than 9. So meaning that when we want to have a sample, alkaline sample, it is very difficult. We cannot use for reverse phase, or even we can never use for the ODS column. And sometimes one of the disadvantages is sometimes the solid support may cause like a catalytic changes in the samples. This is not so normal, but sometimes it happens if you use polymer-based column. Yeah? So that is why polymer-based is not so common, and it is like maybe less, like if you compare the use of the silica-based or the polymer-based, silica-based is about 80% and polymer-based column is about 20%, because the physical environments of polymer is not as stable as the silica. Yeah? Okay, so however, absorption, the main applications of the absorption chromatography, like the column, nowadays is, I can say, not really limited there, but it's more common. We use it for solid phase extractions. So solid phase extraction is very important when we want to do like a pre-treatment of our samples. So this is one of the products sold by Thermo Fisher, one of the biggest company right now. So you can see these are the SPE columns. The columns are usually put on top of here. So usually we do the conditioning of our samples. So when the samples is being put from top of the this syringe, this syringe column, it is a column, but it looks like a syringe. So, and if you look at here, this is like a pressure. So usually we have to do like, we have to use like a desiccator to make it under some pressure so that it will be faster to do the extractions. So this is to reduce the time. So in real analysis, we usually do a lot of pre-treatment of column. Yeah? I mean, pre-treatment of your samples, because the analysis now, everything is so advanced. You don't really need to make, set up the column or whatever, because everything is already in one package. Yeah? So what you need to do is to prepare your sample. Usually to prepare sample takes the whole day. Yeah? Because you have to, for example, if you want to analyze pesticide in, for example, in vegetable. So sometimes, in the vegetable, you have to pre-treat a lot because of the other compounds. And if you want to analyze the pesticide in the vegetable, and the pesticide amount is so low, it's like less than ppm. So the pre-treatment is very important. So we spend the whole day doing pre-treatment. You have to cut the vegetable first, like you have to separate which part to analyze and which part you need to cut. And then you have to homogenize in different liquids, and you have to do the extractions. Yeah? So it takes the whole day. So usually by the time you finish preparing your sample, you just put in the auto sampler. Usually in the company or in the lab, they will have an auto sampler. Auto sampler means there are so many cases like this. You just put the sample and then you just set it and you just program your analysis and you just go home. Yeah. So the next day, the next morning when you come, the computer, everything, they will have the data for you. So, and then you have to spend another day to analyze your data. Yeah. So usually we don't do so much of the separation because the HPLC is so clever now, they will do everything for you. So you just need to prepare your sample. And of course, we still need people to analyze the data because especially when you use LC-mass means the mass spectrometer. It's very complicated. So when you have a very complicated samples, so we spend a lot of time just to read the data because it's very hectic, yeah, and it's a lot and very hectic. So this is just one of the modern applications of absorption chromatography where we use solid phase extractions. So in my lab, we have something more common like this. So these are one-time users like the cartridge, but usually we just buy an empty, something like an empty syringe like this, which is a plastics. In some cases, we cannot use glass because glass will have some compound when we leach inside something which is high. So usually we just buy a disc like this, So different discs will have a different kind of compounds. So this one is for liquid phase. So the disc will be sold like, it depends on what kind of sample you want to buy. So usually we will buy, you can see here, this is 0.45 microns, meaning that any sample which is less than 0.45, we can filter them. So usually we just, you can reuse many times. Yeah. So you can just set like this. And then we can just do the filtration. Yeah. So this is the cheapest, but actually this thing is not so cheap. Yeah. So normally when we buy, they will come like a 10 in a set. So usually I buy 100, like 45,000 っていくらかな。It depends on the
around 5 million here.
5 million, yeah.
5 million.
Okay. So this is,
yeah.
Yeah, this is a big one because this is a 25 mm. So sometimes you can buy the 10 mm, 1 centimeter is cheaper, but usually when we want to do sample faster, we use a bigger one. Yeah? So we just, this is a lower log. So you put the sample inside first and then just set it. So it's very strong. Yeah, you cannot put, it's very strong. So, and then you just filter your sample, then after that you can just turn it and then you can, use another solvent, change your solvent. So this is usually what we do, I mean, in real analysis. Yeah. So anyway, so this is the usual one, and which is a cheaper one, and which is a most common one, and it's very common. Yeah. So anyway, but in recently, solid phase micro extractions, we call it the SPME. This is more popular right now, especially for biological sample. For example, in a crime scene, when there's a crime happening and when you only have a drops of like a blood or something. So in this case, we will bring a syringe and on the tip of the syringe, you can get the extractions. So I have some of my students who are working in the Gifu Prefecture crime lab. So I don't know if you watched the American drama, the CSI, Crime Scene Investigations. So these are one of my favorite dramas. So in this drama, CSI, because my major is analytical sciences, so I like this drama so much because every time they will use GC, LC, and then DNA analyzer, but every time it's impossible because they can get their result in 5 minutes, which is almost impossible. But it's very interesting how they do the analysis, yeah, like what kind of solvent they use, and in terms of when a crime happening, so how do they do the analysis? You can learn a lot from the dramas. And from my student my ex-student who are working in the crime lab, they say most of the time they have to do a lot of DNA testing because yeah, sometimes but in Japan, the DNA bank is not as rich as America, yeah. Even in Japan, we don't even have our thumbprint, like maybe, Fitri know because Fitri was in Japan before. Recently, we just started to have a new ID card for all people, including Japanese. Yeah. Before that, Japanese, they don't have an ID card, So how do you ID yourself? Yeah. For us, for foreigner, we have this alien card. Yeah. We call it alien card. But now the Japanese government is a bit nicer. They don't call us alien. They give us a resident card. Yeah. So now the card is called resident card. It's not, we don't call alien card anymore right now. And from last year, all the residents in Japan, including Japanese, we have this my number card. So we call it my number. My number means your number. Yeah. So sometimes Japanese is very funny. Yeah. They use a lot of English, but it's funny English. So this card is called my number card. So it's funny. But we start to have this my number card right now. So what has been changing is that, when you want to go somewhere, you can even pay anything with this my number card. It's very convenient. Yeah? You can even get your certificate from a combini now. So it's very convenient. But anyway, sorry, talk too much. Anyway, this SPME, it's more popular right now. Due to time constraint, I recommend you to have some reading if you have the time. So this is, I think every year, not really every year, Supelco was the first company who invented SPME. So I think every year they are the German branch of Supelco. They are from Europe. Yeah. So they were the first company who introduced solid phase micro extractions. So if you Google from this Sigma Outreach homepage, they will have like a webinar or something. Maybe you can read, for those who are interested, you can read more about this. I think, it's in the future, this is more popular. And if you want to have some research to do, maybe in the future, you can do research in SPME, which is, I think it's the trend of the future. Okay, so, I finished with the absorption. I will continue with partition. So, like I said, partition is a bit complicated because originally partition, it means like a liquid, yeah. But recently, because the absorption is taking so much time, so what we do to reduce the interactions is we modify another layer of liquid on the support. So the reason why we use different solvent is because we want to reduce the interaction. So when we reduce the interactions here, we can have better selectivity. So better selectivity means that we can separate better, yeah. And so sorry, the definitions of these partitions is based on the partitioning between a liquid mobile phase and a liquid stationary phase coated on the solid support. So the most, the original, sorry, like the first type of separation was actually normal phase. Yeah? Like I talk about it when I talk about the history of chromatography. Z used silica and he separated plant pigments like chlorophyll, xanthophyll, and chlorophyll A. So he separated these four using normal phase liquid chromatography. Yeah? So last week, I shared this slide with you, and then I think I asked you why is it normal phase and why does it call reverse phase? Yeah, maybe you still remember. It's because Z was the first person who made the silica column. So the first person who invented silica, we call that the normal phase. So when we have the opposite, we just call the reverse phase. So meaning that it happens, the first one was the silica, and then it just happened, we call it as just normal phase. Yeah? So, and partition actually involve these two, normal phase and reverse phase. And in some cases, we call it helix. Helix, some people say it's normal phase, but I don't think it's normal phase because we use a different solvent. So helix is a combination of reverse phase and normal phase. Yeah? But anyway, the most common type of LC is reverse phase. Be careful of the wording here. Usually we say reversed phase chromatography. So the main interactions involved in this partitioning chromatography is like the proton accepting ability. Of course, we need a proton donor. Another type is the dipole interactions. And then we also have to decide the electron pair donating ability. And of course, last but not least, the van der Waals dispersion forces. So among all of these five interactions, there are other smaller interactions, but the important ones are the proton accepting ability or the proton donors, meaning that the ability, the columns or the samples able to transfer proton will determine how you do the partitioning. Because when we involve a liquid like a water, so water it's a form of ions. So meaning that the transfer of proton is actually quite important. So by choosing different kind of interactions, we can decide the selectivity. So selectivity here means how we want to separate a certain samples based on their functional groups. So, okay, all right. So this is just another example again, like normal phase, the column we use have to be a polar ones. And then the weak mobile phase usually is a non-polar liquid, and strong mobile phase is a polar liquid. Yeah? So this is actually opposite for reversed phase, where the column has to be a non-polar column, and the weak mobile phase usually is a polar liquid. And be careful here, and the strong mobile phase has to be more non-polar. Yeah? So what is the main difference between the separations of these two? I mean, the selectivity. For example, when we have three samples, for example, sample A, sample B, and sample C. When sample A has the highest polarity and sample C has the lowest polarity. So in terms of normal phase, when we do the separation in terms of times here, so the retention for the sample A will be like the longest, and this one will be the lowest. When we use the reverse phase, which is actually opposite, A, B, C will come opposite. Yeah. So this is something you just need to remember when we have a totally different system, a normal phase and reverse phase. So when you have a different polarity, usually it will go, opposite way, like CBA in normal phase, and then when it's reverse phase, it become ABC. I think I mentioned many times, like reverse phase is more popular. Yeah. Just one simple questions. Why do you think it is more popular? Yeah. Or maybe the column is cheaper. I don't know. Or how about the solvent mobile phase? Yeah. Okay, I'll give you 30 seconds to think. Why is it more popular? San Jubilee. Well, there are maybe three reasons. Three. Well, the main reason is because it can separate non-polar as well as polar samples. Yeah. Like if you look at here, the weak mobile phase is a polar liquid. Yeah. So polar liquid can be many things, but the cheapest polar liquid is water. Yeah. So reverse phase, we can use water to as the mobile phase. But in normal phase, we usually use almost 100% organic solvent like hexane. Or sometimes we just mix 1 or 2% of water. Yeah. But in the case of reverse phase, the weak solvent here is a polar liquid, and usually we use water. So it is also ideal for aqueous-based biological samples. So, well, yeah, as you know, many, our body, more than 70% is water. So a lot of biological sample is actually water soluble. So in this case, it is difficult to separate using normal phase. So that is why it is more popular, because we can use water as a solvent. Another thing I would like to share is this is a list of the solvent we usually used for liquid chromatography. So water here will be the most, at the lowest here, will be the most popular one, and it promotes reverse phase retention. So retention means to hold the sample. Yeah. So on the other words, it means it promotes normal phase elution. Yeah. Elution is to push the sample out. So if you go all the way, this is the epsilon. This is the solvent, the strength of the solvent of the solvent as a solvent. Yeah, sorry, the strength of the solvent. Yeah, epsilon. So you can see water, methanol, isopropanol, and up to here, when we used for retention for normal phase is hexane, which is close to 0. Yeah. So we don't use isooctane so much because hexane is cheaper and is better. So it's easier to use hexane here. So, and in other words, hexane cannot, promote retention of reverse phase. It will elude the retention. If you take a look at the list, it is quite common, yeah, like toluene, benzene, chloroform. But of course, we don't use chloroform so much because it's a chlorine based. We try to avoid the chlorine base as a mobile phase, because if you use HPLC every day, you have to use 1 bottle of the mobile phase. That means the waste is a lot. Yeah. So we try to avoid chlorine based mobile phase. So for reverse phase, usually we will use water, methanol, or acetonitrile. Yeah. So sometimes we mix the acetonitrile with a methanol. It depends on, it's difficult to explain, but sometimes when you need to mix it, it's the separation will be different when we have methanol. But most of the time we use acetonitrile here. And when you use HPLC, we had to use the HPLC grade acetonitrile because we have to decrease the absorption of the solvent so that our sensitivity can be increased. It's difficult for me to explain why we use acetonitrile here because of the absorbance, and you have to try by yourself, then you know what I mean here. If you use the non-HPLC grade, the background noise is very high. You cannot see anything. So in other words, sometimes to choose the grade of the eluent is quite, you need some experience. Yeah? So sometimes you just buy the good solvent, then you can have good data. Yeah? Usually the cheap solvent, sometimes they will not give you so good data because the noise is very bad and because of the impurity. Yeah? So anyway, you can take a look. You can have this list in your textbook or somewhere. It is a common list with different epsilon data. One thing you need to be careful is we do not mix alcohol and water 1-to-1 ratio. Yeah, maybe you might be surprised to know when the viscosity, organic solvent basically has a lower viscosity than water, right? But actually, when you mix methanol with water, like 50% methanol 1-to-1, the viscosity is higher than water itself. Yeah? So that's why we do not use methanol 50% as eluent, because the viscosity is too high and the pressure is too high. Our system will be broken. Yeah? Not broken, it will not give us some good data. Yeah? So usually we choose acetonitrile, which is easier and is better. The viscosity is lower compared to methanol. So in selecting the eluent, usually we have to consider 3 factors. The first one is the type of organic solvent that we need to choose. And then the second one, we have to consider the proportion of organic solvent. And last but not least, we also have to consider the pH of the solvent. So pH of the solvent will be important when you need to separate weak ionic samples like vitamins. Yeah? So vitamins usually is very weak. So you need to have a buffer, and sometimes you need a buffer to stabilize your sample. Another thing you need to consider the pH of the solvent is because of your column. Yeah? Because most of the column we use silica gel, and silica gel basically cannot be, we don't use it with pH more than 8. So in this case, the silica gel will be dissolved, and then your column will be broken very fast. So we do not use pH more than 8 for any HPLC solvent. So this is part of the samples that for the columns of reverse phase. The most common one is the C18. For example, this is a silica gel. C18 means is C, just octadecile, yeah? 1, 2, 3, 4, 5, 6, until 18. So I remember last week, some students asked very good questions. Why is it 18, yeah? It is because of the technical problem of making this column. I think in previously, some people use methyl silica. Methyl means only 1 C, yeah? But it was not good. And then because of the chemicals, some people also use C8. So C8, the next one, sometimes you can successfully make C12, but it is not common. So silica, C8, and then it is C18. Yeah. So this is the technical part of the technique when they do the columns. So this is some of the images like for the silica support. And then you have your alkyls standing like this. So ideally, the stationary phase have to have like have to promote a form of like a barrier, you know, like a phase here, so that when there's a silica like this and the eluent can be trapped in this alkane chains here and to form a layer of solvent. Yeah? So this is where the layer of solvent will have the partitioning, like the interactions between the samples and the column. So this is a different example. For example, this is a protein, which is a bigger one, and this is a peptide, which is a smaller ones. So reverse phase is also very popular to use for peptide separations. Especially now with all the tests and different thing. Sorry, I have a check. Can I just, what kind of solvent can you mix when you have similarity quality and to over issue? So I have a question from Faika. Yeah, she's asking like what kind of solvent we can mix to when we have a polarity. So my answer is, if you do not need to mix, we do not mix. Yeah, we only mix when we want to improve the separations. So chloroform and dichloromethane, it's usually used for normal phase. Yeah. So in some cases, we need to mix chloroform with hexane to improve some separations, like separations for heavy metal ions. Yeah. So sometimes the heavy metal ions, they do not come as an ions. They will come like a compound, like a complex. So when we have a heavy metal inside a compound, then usually we use the normal phase to do the separations. So in this case, when there's a different strength of the heavy metal ions, we have to use a different strengths. So usually we mix chloroform. Your question, this is a very difficult question, yeah, because somehow it's difficult to decide which one to use when the polarity is the same. In this case, we will beside the polarity, we also consider the functional group of the sample. Yeah. So you will see which functional group will have better the interactions. Then we will choose that solvent. But polarity is the main thing to choose sometimes. Yeah. The easiest, if you do not need to mix, we don't mix. Yeah. So we only mix when we want to improve the selectivity. Good question. Thank you. If you have any questions, feel free to put in the chat. Today I try to use 2 monitors so that I can see your chat messages. Okay, thank you. So reverse phase C18, I think I'm not sure if you go to your lab now, I mean, if you have a HPLC system, if you check your column, I think 99% your column is the ODS. This is a C18 column, yeah. Because ODS is so popular now, and in any labs usually, and it's cheaper to have an ODS column. So, and if you, sorry, I will continue with these 2 cases, yeah. Why these 2 cases is, well, actually, yeah, there are many other examples. I will share some other slides later. So the important thing is I want you to see is the standing, like we call it the phase, how do you say it? The alkane, yeah? Because alkane C18, it will stand. We assume C18 will stand in the solvent so that they will provide a place to hold some part of the solvent to form a phase. Yeah. But sometimes, in some cases, the phase will collapse. Yeah? The phase will collapse means it will not go straight, it will go somewhere else, depending on the solvent. That is why if you have a different solvent like C18, it is a hydrophobic phase. So when you increase your water, or when you increase your organic solvent, you can control the thickness of this phase. Yeah? So when you control the thickness of this phase, then you can control how long or how fast your sample can be retained on the surface of this column. And so hi. Sorry, I don't know whether if you understand what I'm trying to say. So, okay, this is C18. Yeah? So, meaning that the C18 will have they will stand straight, and this will form another phase, and it will retain the two different things. Yeah? So usually for protein and peptides, they are hydrophobic samples. So usually we will use reverse phase, and it is very good and very easy to separate proteins. The main difference between proteins and peptides is the molecular weight, of course. When we digest protein, we will have peptides, which is smaller. So when it's smaller, it is actually quite difficult to do the separations. Is it possible that one peak had more than one compound? Yeah, sometimes, sorry, I have a question that is it possible that one peak had more than one compound? So it depending on your separation conditions. Yeah. Yes, for real sample, it is possible. Yeah. One peak can contain more than one compound when they have exactly the same retention time. So yes, you can. Yeah. So in this case, how we want to differentiate whether this peak has only one compound or two compounds is we will do mass spectrometry to confirm the molecular weight. So usually if you use UV, it's very typical to have real sample analysis, but in some cases, it is easier when we can separate them. Yeah. Yes. Sorry, I hope I answer your questions, Dr. Rusli. But okay, thank you. Okay, yeah, it is possible, especially you are in pharmacy, right? I have experience with separations of drugs, and it is very difficult. Yeah. So at the time, I asked my student. He was a PhD student from a crime lab. So we use capillary electrophoresis. So I will talk about electrophoresis in the final lecture. So, well, personally, I don't really like electrophoresis, but sometimes it is easier to use electrophoresis to do the separations for drugs, especially because we can increase the capillaries length, and we can also use different buffer to have different directions with the drugs. Yeah. Yeah, I think maybe you want to separate some drugs which has, yes, where if you use HPLC, it is possible one peak you can contain more than one compound. Yeah. Yeah. So in order to confirm, you have to use a mass spec to confirm the molecular weight. Or in other case, if your compound has a fluorescence, you can also use change the UV detector to a fluorescent detector. So yeah, I will share with the student about detectors of HPLC when I talk about HPLC later. So yeah, hopefully there will be some good questions also, because it's normal for me, and sometimes I don't know what is the problem when you do the real-time analysis. Yeah. Okay. But okay, I hope I answer your questions. Okay. All right. I will continue with this reverse phase. But anyway, the column ability now, it's involving a lot. Yeah. So today I saw that. Oh, I wanted to copy one slide with the real sample application. Sorry, I will share another slide. Please wait. Alright. Alright. Sorry, I will. No. Sorry, I wanted to share some the chromogram we do with some real sample analysis. I'm sorry, I don't know which one it's. Sharing. While waiting, if you have any question, you can ask questions. Oh, sorry. Oh, sorry. My computer freeze. ちょっと待って. Please wait for a moment.
コンピューターが疲れましたね、先生。
ごめんなさい。
全然大丈夫です。時々ね。
Yeah, it's a bit, sometimes it's just, I want to share with a real sample analysis, but this is sometimes difficult. どこ行ってしまったかな。そうだね。OK。Well, I don't know, like, is this drink is being sell in Indonesia or not? But I think many of you drink tea because we want to, you know, like to take the catechin so that we can, you know, reduce some fat. Yeah. So actually, these drinks in Japan, when the drink is very is approved, is a healthy products, we will have this mark. Yeah. So this mark stands for certified healthy products. So this tea, we call it the healthier. So it's a healthier tea. If you look at the catechin, we call in Japanese we call catechin. Catechin here is 540 milligram. So 540 milligrams. Maybe you think milligram is not so much, yeah. But if the catechin is so high here, it is actually so bitter we cannot drink, yeah. But in order to make this healthy tea and healthy water to be easy to drink and to be healthy, there is we use cyclodextrin. So that cyclodextrin to have this complex, there will be like an inclusion complex. So the bitter component here will be turned off. So meaning that when we drink this tea, it is not so bitter. It is actually so sweet. Yeah. And these products actually is selling so much, you know, it's like 300 billion patent. And because there are some rival company, of course, they say, they put on the internet, say these products, actually they use the cyclodextrin, and this cyclodextrin is actually very bad to your health, and you will have a liver disorder problem. So many people, when we listen to this kind of we don't know whether was it a fake news or not. Yeah. So many people will suspect, oh, maybe it is not good to our health. Yeah. But anyway, in our lab at the time, almost all of us drink this tea and it's so good to drink. But when, sorry, this is in Japanese. When we look at the label here, of course, they will not write cyclodextrin, yeah, because they don't want to give you the impression of the chemicals. So they use another word. They use it oligomer, yeah? Kanjo oligoto means like a sugar, yeah. So when you look at here, oh, it's sugar. So you will think it is nothing, yeah. But actually, cyclodextrin, there are three types of cyclodextrin, yeah. So one is the alpha, and one is the beta, and one is the gamma. So alpha means cyclodextrin, like these compounds. Each cyclodextrin is composed by 6, 7, or 8 glucose. So when the glucose is different, you have a different one. In Japan or in other countries, maybe we do not have a regulation for cyclodextrins, but in America, cyclodextrin is actually listed in one of the regulation. Yeah. So for an adult with more than 60 kilogram, the limit for beta cyclodextrin, beta is with 7 glucose, which is a bit more dangerous compared to alpha and gamma. So only beta was listed in the America food regulations. So in an adult with 60 kilogram, you cannot consume more than 10 grams of cyclodextrin. So when I tested with a reverse phase column using indirect detections here, this is the healthier tea. Yeah? So the same peak with the same retention time is the compound peaks. So meaning that in this tea, there is no beta cyclodextrin. Yeah? There's only gamma cyclodextrin. So meaning that this tea is safe. Yeah? So in another case, I find the same sugar they put here. Maybe, I don't know how many of you like sashimi. So this one is the wasabi. Yeah? If you eat sushi before, or if you eat sashimi before, this one is like a, yeah, but it's very hot. Yeah? I mean, it's different than the spice you use in Indonesia. It's very different. So in order to reduce the pungent the effect of this wasabi, the company also, they put the cyclodextrin. Yeah? So I tested this. It was very difficult to do the pre-treatment because I have to filter this wasabi with this one. And for one sample, I have to use 10 to do the filter. It was so bad, yeah, because it stuck all the time. So I have to use 10 to do the pre-treatment. But anyway, when we tested, from the result, we see there were some beta cyclodextrin. Yeah? But when I calculate the amount of beta cyclodextrin compared to the amount that we can take, like I say, one healthy adult can take 10 grams. Yeah? So in one tube, only contain 0.1 gram cyclodextrin, meaning that as long as you don't take more than 10 tubes per day, that means you are safe. Yeah? It's impossible you want to take so many wasabi in one day. It's impossible. So meaning that this is also safe. Yeah. So this is the example that we use in our lab. Not so common examples, just some applications in food. Yeah. I also have many examples, of course, in environmental analysis, but because of time, so I will not share. When I have the time later, I can share other results. So this is one of the examples. We use reverse phase to do some testing. Yes. Oh, I have some questions. Sorry. What is the meaning of purity in DAE detector? Can you use it for identify? So ne. It can be, I didn't pick my one compound. So okay. Okay, so I have done. So I hope that the surface of paper chromium is covered by water. So if you want to use it, we need to more polar solvent like acid. Pen paper chromium. Okay. どうしよう。determine index quality by mixing solvent to improve the selectivity. Okay. First, so Dr. Zaldi, you asked about DAD detector, yeah? Yeah, DAD detector can detect most of the thing, yeah? It's, but it is not so selective. Yeah, I mean, depending on your condition, yeah, because I cannot, if you have the chromatogram, maybe I can comment after I see your chromatogram, but DAD detector will, you can choose a different wavelength and for different compounds, then you can identify them based on their wavelength of the absorbance. So in this case, you need to know your sample's absorbance first, the wavelength. Then in the DAD, you can use that wavelength, like higher wavelength for certain compounds. Then you can have a more selective detection. So if your wavelength is lower, you will see a lot of peaks. So if your sample can have a higher wavelength, then you can use the DAD detector. Yeah. Yes. I hope I answer your question, yeah, Dr. Zaldi. And then for another question is that paper chromatography. Yes. So usually paper, paper itself is from cellulose. So usually many people, when you want to increase the separations, you will use another solvent so that you will have a two-phase. Yeah? When you have two-phase, you can have at least two interactions. Then you can have better separation. Yeah? Just use paper and water. The separation is very minimum. Yeah? You can only separate sample with very different nature. But if you want to separate a more higher sophisticated sample, then you have to increase the polarity of the paper. In this case, you will use another solvent on the paper so that you can form a two-phase and you can form a different affinity. Yeah, this is it. It's yes. Normally it's something like this. Yeah. Yes. Another question is if you can determine the index of polarity after mixing it, you can, yeah. But usually it is very difficult to determine after mixing, yeah, because it will be different. Yeah. But nowadays, many company they have a very good list. Yeah. So I think Merck company, they have a good list of different solvent with different index and different epsilon value. Yeah. So they have a very good table. I think it's on their homepage. Yeah. If you can get that table, then you can try to estimate what solvent you can use for your eluent. Yeah. What should I do if I got result of compound I have bad separation? Resolution of compound with bad separations. So bad separations, when your separation is bad, you have to see your retention time. Yeah? So if your retention time is long, but your separation is still very bad, that means there's nothing you can do. Yeah, your column is a problem. Yeah, if your retention time is short and your separation is not good, you still can improve by changing the solvent. Yeah? So sometimes it's a limitation of the column, or sometimes it's a limitation of the solvent. So you can determine the separations. First, when the separation is good, then you have to see the retention time. If the retention time is already so long, but it is still so bad, that means the column, we have to improve on the column. In this case, you have to change the column, or you have to change all the eluent. Yeah, that means this eluent is not able to have good separations. But if your retention time is short, and you can still improve on the separation by using a weak solvent. Yeah. And you also have to see whether when the separation is not good, whether your peak is broad or not. Yeah. If your peak is already so broad, that means it's very difficult to improve. Yeah. You almost impossible to improve. Yeah. So sometimes when you want to test whether this eluent is suitable or not for your column, you can see the system peak. Yeah? System peak means you can inject the blank sample. When you inject the blank sample and your peak is very sharp, whether go down or go up, that means this eluent is suitable for your column. Yeah? When you inject a blank sample, like a solvent blank, like a blanco, and the peak is already so broad, that means this eluent is not suitable. Yeah? So you can try by trying different, by looking at the peak shape, you can actually have a lot of information. Yeah? Sometimes the shape of the system peak also give you some information. So if you mix some buffer will come in the middle of the chromogram. If you become so JAMA, JAMA means if you disturb all your separations. Yeah? So in this case, you have to use a buffer concentration to move the buffer peak somewhere. So in this case, sometimes we add a small amount of organic solvent in the reverse phase eluent, like add a small amount of acetonitrile, 10%, so that we can move the buffer peaks to somewhere else in order not to let the buffer peak to disturb our separation. Sorry, I hope I answer your questions. Can the synthesis product like food guarantee our health and safe to consume by the people? Yeah, usually there is a synthetic. It depends on what kind of synthetic food. Yeah, that's why and usually it's better to buy organic food. Yeah, but somehow we cannot avoid to take so much additives in food. Like we cannot avoid not eating the instant noodles. Sometimes I still like instant noodles because the taste is so good. Yeah, and sometimes I still ask my friend to send me Maggi mee from Malaysia because I like the Maggi mee. I don't know if you have Maggi mee in Indonesia. So because of the taste, it's like we still like it, but yeah, you have to try to avoid the additives. No additive, it's actually good. Yeah, I don't know. It depends on individual. Like now, some people say vaccine is good, but some people say vaccine is not good. Yeah, so it depends on individual. Like some people say engineering modified food is not good. But to make the food stronger, we have to modify their genetic informations so that we can have more products like corn, like the soybeans. Most of the soybeans are engineered modified in some cases. Yeah. So it is difficult, to determine whether it is good or not. But usually we try to avoid. Yeah. Yeah. It is best to eat salad. I don't know. Salad just like raw. That's why sashimi is actually so healthier. Maybe the Japanese can live longer is because of the food, less oil, less burnt food. And maybe you learn in your other biology or organic synthesis or organic class, when we burn the food, the protein will turn to like, the like burnt proteins will actually make our body more oxidized. Yeah. So when your body more oxidized, you will have, more wrinkles, like you will have, you will look older. That's why in sometimes there was a time, when there is a company, Suntory. Suntory is one of the biggest beverage company in Japan. they produce you know, hydrogen water. Yeah. So meaning that if you drink the pure hydrogen water, you can reverse your body. You can, you know, like make your body less oxidized. Yeah. That means when you drink more of that kind of water, you can actually make your face or make you look younger or your body become better. But yeah, it is good to drink sometimes. Yeah. I mean, but it's quite expensive to maintain. But I can say that if you can have less burnt food, then you can reduce a lot of oxidation in your body. Yeah. So yeah, some people ask me like, you know, why do I look so young even though I'm not so young? I don't know whether this is a compliment or not, but I just tell them I eat a lot of salad and I don't use oil and so much. And I don't eat sugar so much except cakes. I love cakes, of course, cakes and chocolates. But beside cakes and chocolates, when I cook or whatever, I don't put sugar and I don't put so much salt. Yeah. I don't even remember when was the last time I bought sugar or I bought salt. Yeah. Because normally I just eat them as the original taste. And sometimes I add some soy sauce, but most of the time I don't put so much sugar and salt in my food when I cook. Yeah. And I eat a lot of salad. Yeah. Sorry, this is out of the topic. Yeah. But anyway, just in case you are interested. Yeah. So yeah, I'm sometimes when I look, there's some popular products, and when people say it is not safe or something, I usually I test myself. Yeah. So I will buy the products and I will test it in my own system to see whether it is correct or not. Yeah. So in this case, the cyclodextrin, it was not correct. Yeah. So you can safely drink this healthy water. Yeah. But it is not cheap. Yeah. It is not cheap. Yeah. Anyway, I will continue with sharing my slide for today. So just now I talked about reverse phase column. So, but right now, most of the maker or company, they will make core shell column. Yeah. So core shell columns is something. Okay, core shell column is something like this. Yeah. So in the old days, we use total porous materials. That means like the total porous means something like this. Last week, I talked about the Van Dimter parameters. So when we have a total porous, that means the sample can go through, I mean, the longer time, they will spend longer time because there are different path length, they will pass through the columns. But core shell means the core is non-porous and only the surface is the porous. The surface determine the separations. Yeah? So this is also a way to reduce the separation time and at the same time to maintain the separation by coating the porous materials on the core. So for example, the core cell is the purple line and the traditional total porous is the less purple line. You can see the retention time is reduced a bit here compared to the one, this is number 2. Using core shell is actually faster, and when you can elute something faster, usually the broadening of the peak will be less and you can have a higher sensitivity. Compare, if you look at number 1 is too big to see, but if you compare the number 2 here, you can see the traditional total porous will have a broader peaks, and number 3 here and number 4 here. So you can see by using the core shell, the resolution as well as the sensitivity is reduced, is increased, I mean, it's improved. Yeah. So this is one of the recent trend in making column particles. So another type is, I remember last week I talked about, I'm trying to make C30 columns. So sorry, this slide is in Japanese. And just want to share the difference between the C18 and the C30. So sometimes when we want to separate, like this is a ribonucleus, insulin, cytochrome, and then this is more like proteins, yeah. So we usually separate these kind of things in reverse phase, yeah. So like I say, sometimes when it is standing, it is good, yeah. But sometimes it will have the collapse phase like this. So this is usually how we can control the phase by using different solvent. So comparing the C18 and the C30, you can see maybe it is not much different, yeah. But the resolution between the peaks number 2 and peaks number 3 is actually improved. So actually C18 is more popular and C30 is not so popular. But sometimes now some people are trying to make C30 because if you can successfully control the phase here, there is a possibility you can do the separation by only water, yeah. We don't use organic solvent. So yeah, there's one company right now, they are selling the C30 products. So far, there's only one company it's have this pattern, yeah? And many people who wants to use will have to buy from this company, yeah. So meaning that if you can, you know, make something which is having a special kind of selectivity, you can sell something, yeah. So sorry, so this is the last slide for today. So I would like to have more questions if you want. So while waiting for the questions, I will find some slide that for the real sample analysis, like the environmental analysis. Yeah. Got it. Okay, thank you. Okay, Putri, I want to ask something. Can you recommend some books that you use as guidance for this subject, or like especially the one in English? Oh, so okay. I think in the syllabus, when I read the syllabus that Mora have prepared, I think he has mentioned some books in the reference, in the final part of your reference. So in the list here, I think number 4 by Scott is very popular. So if you want to read something from Scott, you can. But this is normally in the fundamental of analytical chemistry. For me, my favorite is this book, yeah. Analytical Chemistry by G.D. Christians. So G.D. Christians, well, this is an older version, yeah, like the 6th edition. I think now they have the 7th edition. If you buy the latest one, Gary Christian, they also include the latest data science method, how to use Excel to do the chemometrics. So chemometrics means is a kind of data science method to estimate the optimized condition for your separations. Yeah. So I think in one of the lectures, Mora has arranged to have a webinar together with Dr. Rafi. So that Dr. Rafi, he's expert in chemometrics. Yeah? I don't know what is he going to present on that day, but he's an expert in chemometrics, which is one of the latest. I can say it is easier, you know, when you do not have a system to do the separations. So you can estimate first, then you can propose, you can save time to do the separations. Yeah. So yeah, this is the book that I usually use. And Gary is, he comes to Japan often. Yeah, actually I was going to email Gary because almost 10 years ago, he visited Gifu. I was going to show him some. This is, uh, actually, this is Gary. Yeah. So, and he visited Gifu like 10 years ago on in December together with Sue. Sue is the wife. If you read here, you know, so he will write here to Sue, you know. So if you look here, I actually got the signature from Sue when she comes to Gifu. Yeah. So this is one of the, I don't know if you can read here. So Gary and Sue, they are so good together. And then I received the message from Sue when they came to Gifu. I said, please sign autograph, sign my books. I also, of course, I also have Gary's signature somewhere. Yeah, somewhere here. So he wrote for me also, Gary. That's why I always keep this book. Yeah. So yeah, this is my lab members. I am not in the photo because I was the cameraman. So this is my my boss, Professor Takeuchi, and Professor Sakae. He is the one of the main person in FIA. FIA means flow injection analysis. So he was the former president of the flow injection analysis of Japan. And my boss was the former president of the ion chromatography. So that's why my major is also ion chromatography. So I will talk about more about ion chromatography next week, maybe. And maybe Rafi is so different now. So that time Rafi was so young. If you know Rafi, so, and also Ime, also my good friend. I don't know if Fitri knows Ime as well. Maybe yes, yeah.
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 And then there are some people who like Rosa from UNRI in Riau University, and then Siswoyo. I don't know where is she. He's in Bogor now, but not in a university. And Femi, maybe still in Padang. Yeah. So their chemistry, maybe, I don't know, maybe you know them. But anyway, Ime and Rafi, we are quite close. And Rosa, we are still in contact, very often contact. Yeah, and Ime, because our birthday is so close, we always celebrate birthday together when we were in Gifu. So and actually I took Sue and Gary to a nearby Japanese restaurant here. There's a Gifu Castle here. I also take them to Gifu Castle. So this is the how to say, the owner of the castle happened to be there. Yeah? So it was so surprised. So we just took a photo with the owner of the Gifu Castle. So and then yeah, from the castle you can see the whole of Nagara River. And they were so funny because they like to take photos like this. So this is in Japan, there are so many models like this. You can put your face and take photos. Yeah. So I took a face of the Gary and Sue. This is Nobunaga, is one of the famous general in Gifu. So Gifu was very popular before because it became one of the main for the emperor in Oda Nobunaga. So if you come to Gifu Station, you can see there is a big statue of Oda Nobunaga. It's coated with golden kimpaku, the golden, how to say, it's coated in golden kimpaku, like a slice, like a yeah, slice, yeah, something like that. Yeah. Anyway, sorry. I have the last slide, baseline computer is not played. What's happening about this? In the last slide. Soka. Last slide. Sorry, which slide was that? You mean, sorry, I have this question. Okay. Mm. So I will, okay, anti-chemistry PDF drive. Oh, すごい. This is the GD Creation 7 edition. So fast you have this. So the student can read, yeah.
Yes.
The last slide, baseline chromatograph is not, what's happened about this? The last slide,
The comparisons between C18 and
C80 and
C30.
C30,
Yeah.
yeah.
Yeah. Yeah, that one.
Okay. You mean the you mean the C30 here or the, is it the C18 or the C30?
Maybe the baseline, maybe.
Yeah, you mean the C18, right?
Mm.
Yeah, C18, yeah, it's the separation is it's considered separated. Yeah, C30 actually improved a bit. I don't have the data here, but this is baseline separated, yeah. But in some cases, actually these samples, it's quite difficult to separate because they will become broader. So like for example, if you look at the sample here, it's only 3 centimeter like this, yeah. It's a short column, yeah. So, and if you look at the retention time here, it's actually less than 8 minutes, less than 10 minutes. So usually when we want to separate some proteins, we usually use a long column like this, and it will take about 40 minutes, 50 minutes. Yeah. So yes. So meaning that, yeah, if you look at the time here with these samples, meaning that we can call this like a high throughput separation. Yeah. Maybe it's a bit difficult for the student to understand what is high throughput. Yeah. If you read some papers, if you have time, you can try to Google shotgun analysis. Gun means for gun. Yeah. So shotgun analysis now is very popular when we want to separate proteins and biological samples. Like I say, people want fast results with good separations. Like shotguns meaning that using column like this, very short columns, 2 centimeter, 3 centimeter, 5 centimeters to increase the separation efficiency and at the same time to reduce the separation time. So that is for maybe for some reading shotgun analysis. Sorry, I hope I answer your questions. If we have chromatograms.
Maybe about the baseline problem. Usually it's played like this, but it's a kind of, how to say, there's elevation, yeah?
So on. Yeah. Usually when the baseline is like this, usually it's because of the, sometimes you can reduce this by using a different wavelength. Yeah? So maybe if you have, you can check your wavelength. Yeah? If your wavelength is around 220, 230, then it is normal to have a baseline like this. If your eluent contain something like a mixture between acetonitrile and water. Yeah. So sometimes it also depends of your sample. Yeah. This sample is usually like this. Yeah. So, but if you have, sometimes it's also because of your detector. Yeah. So yeah, if the detector is having some weak lamp, because the lamp of the detector, usually when the company they sell to you the detector, they will say you can use for 2000 hours. Yeah. But in reality, we use more than 5,000 hours because it's expensive. Yeah? So sometimes when the lamp of the detector is old, your baseline will be kata kata like this. Yeah? So you can test it when you switch on the detector. Yeah. So sometimes in some detector, you will have a panel. You can check the lamp emission. Yeah? So when you put on the switch, don't go somewhere, look at the panel and check the emission. So the detector will say lamp, checking lamp emission, then they will tell you good or not good. Yeah. So when it is good, usually the noise will be less, but sometimes it will become like poor, P-O-O-R, poor, meaning that you have to get ready to change your lamp. Yeah? So, but usually I do not order the lamp so fast because the lamp, it's like same like the light. So once you order, it's already getting old. Yeah? So the longer you keep the lamp, it will become old. So it's not good for the lamp. So normally I will order the lamp just right before I want to change my detector's lamp. Yeah. Yeah. Sorry, I hope I answer your questions. You can check your detectors. Usually there is a seal at the side of the detector. You can check the lot number, and you can Google in the makers, and then you can know when is the production. Yeah? So when the production is old, maybe you need to see whether the lamp you need to change or not. Yeah? Sorry, I don't know if this is what City was asking. Yeah? I mean, not plate at all. なんだろう。
Maybe in the normal case, the chromatogram is always like this, horizontal, right? But in your case, yeah, the chromatogram a kind of elevation. So is it a kind of the normal chromatogram, or yeah,
No,
something
no,
that
no,
you
no,
just
no,
mentioned?
no, 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 no. This one is sorry. This one is そうだね、そうだね。
Hey, let's repeat the question.
This is a question. Okay, okay. You mean the baseline is not straight, is like this. This one is because of the pressure, yeah. Yeah. Pressure of the column. So yes. So when your system pressure change, you have drift. We call it a drift, yeah. So the drift will go up. Sometimes the drift will go down, yeah. So this is because of the column pressure. And when you do uh, separation like this, you will have a lot of drift most of the time if your sample is involved biological sample. Yeah. Sorry, I hope this is your question. Yeah? This is the answer for your questions. Yeah? This is because of the pressure, yeah? Pressure of the pump. Yeah? Another thing is, I did not write here. This is also being done with gradient illusion. So gradient illusion means we use two different solvent as a mobile phase with two different in this case is acetonitrile as a B, and the A is 0.1. This is the one of the acidic buffer. So usually B is stronger to separate faster, but we need to reduce here so that we can do the separation. So this is a gradient illusion. Pressure is different, gradient is different. That's why it will have a different drift. Good question. If run with similar solvent system with similar sample, but we have different retention time. Oh, the similar compound. If you only have one sample, then you can, yeah. That's why it depends on usually if your system is okay, usually if you have a same solvent and the same sample with the same column, usually you will have a same retention time. Yeah? So oh, you mean you want the PowerPoint of this slide? Yeah, yeah, I can share. I will put it somewhere. I thought because yeah, Mora told me it's already recorded somewhere, so I thought maybe you can see from the recording. Sometimes it's a bit embarrassing, yeah, when it's recording. So okay. Anyway, so then today it's mostly about these two. Well, next week I hope I can share more about these three topics. Maybe it's a bit more. That's why maybe I might not have time to share the real sample analysis, but I will try to put some in. Okay. Well, if you have time, maybe you want to read a bit about ion exchange chromatography or maybe XCC. So SCC, it's more for size separations, especially involving proteins kana, the usual thing that we do. And affinity, it's depending on what case. Usually it's for like enzyme and also very biological samples, yeah. And ion chromatography is more for environmental samples. So yeah, next week will be a mixture of this chromatography. Yeah, if you have time, maybe you can read a bit and then let me know some questions. Yeah. But anyway, yeah, we can, yeah. Okay, your sample show in 7 minutes, but based on literature must be shown in 6 minutes. Maybe your palm is not correct, yeah. How about your flow rate? Is your flow rate the same as the literature or not? So that means, Siti, you are doing the real sample analysis or all condition is the same. So then, yeah, maybe you can wash your column, yeah. So sometimes some people say it is not good, but sometimes I wash my column with acetone. Yeah. Don't wash too long, just wash a bit and then yeah, try to wash with other organic solvent. Yeah. But yeah, if it's supposed to be 6 minutes and you get 7 minutes, it is a bit too long. Yeah. I mean, if 0.1 is still okay, but 7 and 6 is a bit too long. Yeah. Maybe it's if you have only one sample and you are sure this is the only compound, then so that maybe the depth volume maybe is different. Depth volume means when you connect your column to the detector, there's another small part, like a connector part. Yeah. Please check your connector diameter. Is it big or small? Maybe the connector of the depth volume is not the same. Yeah. I cannot think of other reason. Yeah. If your condition, everything is the same and your yeah. Another possibility is your column's ability is different. Yeah. So sometimes even if you have the same ODS column with the same dimensions and the same length, sometimes the amount of ODS on the silica gel is different depending on the company. So this is, of course, is the company's secret when they sell the column. So sometimes when you make a column, you also have to do the end capping. We call it end capping, means when you do the reaction between the ODS and the silica, there will be some extra silanol materials left on the silica. Yeah? So when the extra silanol left on the silica, this extra silanol will have extra interaction with your sample, and it will cause your sample become broad sometimes. So when some company, they have a different, we call it the end capping technology, then they will have a way to end cap the silanol base. So this is secret of the company. We cannot know how they do the end capping. But in my lab, I use 20% sulfuric acid to do the end capping. So for us, we can have some reduce some silanol base. Yeah. Maybe Siti, you can check your with another ODS column, maybe. That's why this the only reason I can think of. Yeah, one is the capacity of the ODS is not the same, even though the same size of the column. Another possibility is the connection between the column and the detector, and between the column and the injector. Yeah. So check the dead volume. Dead volume means the volume that is outside of the column. Yeah. So when the diameter of the connection tube is big, it is not good. You have to change to another tube. Yeah. Other possibility, I don't know. Yeah. Yeah. If your concentration is correct. Yeah. Yeah. Because 1 minute is quite long. So yeah, maybe, yeah. Okay. I hope it will help you with your separations. Yeah. So do we have other questions? Anyway, I will send my the so done. Well, it is not so good, but I will give the slide to Mora later. Maybe Mora will upload somewhere for you to download somewhere. Maybe. Okay, Kana. Okay. So thank you for your time. I don't know, we have what, 99 participants, but
100, 105. Yeah.
I don't know whether is it good or not, because Mora told me there were like more than 100 something registration. Yeah. So
Yeah.
it
Yeah.
means,
So sometimes the schedule was, how to say, overlap with.
yeah, maybe, yeah.
But anyhow, if the registrations around 100 something and the attendance over 100 is already great.
Okay.
So it's mean over 70% something.
Okay, that's nice.
Just for the online meeting. Yeah.
Yeah.
Yeah. Anyhow, very very great, Prof. Yeah, it's a wonderful lecture, I guess. So you provide the comprehensive and systematic lecture. And also, how to say, the best practice, yeah, that you been experienced. Also, you share with the students.
Yeah. Sometimes it's
yeah.
it's actually in theory it's so easy, but
Yeah,
in real time it's so difficult.
yes. Because many problem include the troubleshooting never available in the textbook, right?
So nice, so nice. Yeah, it is. Yeah,
It's
it is.
solved only by the experience. So yeah,
Yeah, it
I
is.
guess it's amazing. So thank you, bro, for kindly
Oh, thank you.
providing
Thank
yeah,
you.
that one. Mhm.
Thank you. Okay, I will
Alright.
see you next week, Anna.
Alright. Hai, mata
Bye.
raishu.
また来週
Internet
ね。
sensei. Hai, arigatou.
はい。ありがとうございます。
Hai, mata raishu.
はい。
Okay, everyone. So this the end of the lecture. I'm not sure Mora is here.
He has a training, yeah.
Ah, I see. I see. Yeah, yeah. Because he is now in the period for the new employmentship.
Oh,
Yeah,
really?
yeah,
That's
yeah.
nice for him.
Yeah, and this week is the last period for that. How to say the a kind of the workshop, and after that, yeah, he can obtain the how to say 100 full time.
Oh, okay.
After that, yeah. All
That's
right.
nice.
Yeah.
By the way, Japan government has announced yesterday to let international students to come to Japan from now on. Yeah.
That sounds good.
Yeah,
That sounds
there
good.
are so many people who are waiting to come to Japan because of
Yeah.
COVID-19, so it has been delayed. So
Yeah.
the MEC students, it's already will get their ticket soon, and they will come to Japan end of this month. Yeah.
I see. I see.
Then,
Yeah.
yeah. Then after that will be the private student, and then
Mhm.
some other maybe government sponsored students. So from
Yes.
this month until December,
Yeah.
everybody will be able who has the COE, will
Yeah.
can have the visa
Mhm.
can apply for visa and then can come soon. Yeah.
Yeah.
For tourists, no, still cannot. Yeah.
Yeah. Yeah.
Yeah.
In the embassy also here, yeah, the embassy was closed for temporary due to the
Yeah.
COVID. And
So
for some how to say student candidates who already earned the LOA, yeah,
yeah.
finally they they have to postpone until the
Oh,
embassy open that one. And maybe
okay, okay.
the new LOA need to be issued again, yeah. But
Oh,
anyhow,
okay.
it sounds great, Prof. If
Oh, but it depends. It depends on the date when they issue the COE. Yeah, because our student they actually get the CO certificate of eligibility last year. Yeah, so those who receive from October last year until this year is still valid. Yeah, even though it's already expired. Yeah.
I see.
Yeah, it's written in the homepage. Depending on the period when you got the COE, it's automatically extended more than 6 months. Yeah. So for our student who actually received, who actually was supposed to come last year, they still can use that to apply for the visa. Yeah. So
Yeah.
there's a period from this period until this period, then it is still okay to use now. But for after or before when, then you have to apply again. Yeah. So they announce in the homepage. Yeah.
Yeah, that sounds great in such case, yeah. So
Yeah. Please
that's good.
check the date, and then please check the
Yeah.
homepage, and then
Yeah.
please call the embassy. They will know. Yeah.
Yeah. Me either my former supervisor also asked me if whether I have a time to visit. Short visit there, yeah. It's really how to say hardly waiting, yeah, to enable
Yes. Yeah.
to come to Japan. But maybe as you mentioned, for only for the special purpose.
Yeah. So
Not
on.
for
So on.
vacation at the
Only
moment.
for the special purpose. So on.
Yeah. Hopefully after New Year's, the conditions getting better.
Hopefully,
In
yeah.
Japan
Hopefully.
as well, yeah. Here in Bandung as well. I'm not sure, but the number of cases that been reported, I guess, is how to say seriously declined. Yeah. So hopefully this is a good indication.
Yeah, I hope so.
The COVID-19 pandemic, and yeah, we can back to the new normal, and yeah.
Yes.
Hopefully also someday I can visit you, problem.
Yes, please.
Yeah.
Ikifu is a small city, but it's a nice city.
Yeah. I've been twice in Gifu and try the unagi.
Oh, okay.
There's unagi there.
Yeah, very good. Yeah, and ayu fish also.
Yeah. Kontani oishikata.
結構美味しいですよね。
All right, Prof. So I guess
はい。
we already come to the end of the lecture.
はい。
So to
はい。
all my beloved students and also other participants who already joined with us, thank you so much for your great attendance today. And it's wonderful. We have many great interactions, yeah, with many questions, and from that activities, even we can learn something new. And the experience is how to do a kind of troubleshooting when you got or you are facing a kind of problem, yeah, in the chromatography experiment. So I do believe this really wonderful lectures, and if you are missing for some point, you also can refer to our YouTube record, yeah. You can fully, yeah, you can fully rewind the video if you miss some explanation from Prof Lim. Again, Prof Lim, thank you so much. It was great to have you today, and looking forward to see you again next week.
はい。
お疲れ様でした、先生。
はい。ございます。